And we have good old Anne. A 620-meter long, measured when the spaceship is stationary, spaceship passes by the Earth. What length would people on the Earth say the spaceship was as it passed the Earth at 96% of the speed of light? Well, length. Is this asking me to find L or L0? So I'm going to write down L equals question mark. So that must mean they gave me the original length, L0, the original length. Oh, yeah. 620 meters. I'd love that if someday we did have spaceships that were that long. Although the ISS is about 100 meters long, but that's mostly because of the big solar panels. The actual ship itself is not quite that long, but still pretty cool. V is 0.96 C. So the length equation is L equals L0 times the square root of 1 minus V over C all squared. Yes, I think that's right. Which is 620 times the square root of 1 minus 0.96 C over C all squared. Is there a C on the top? Is there a C on the bottom? Those will cancel. In fact, it's going to be 1 minus 0.96 squared, square root, times 620. I think I can do this in one fell swoop. I think. Let's find out. 620, square root button, bracket, 1 take away 0.96 squared. Do we get, 173.6? That's a fluke that there's not a bunch of decimals. I'll take it. Units. Meters. Okay. If you got that, 2 out of 2. Otherwise, I would probably go half mark for the equation, 1 mark for the numbers, half mark for the answer. And it'll probably be that way for most of the rest of this quiz. What are they asking me to find in number 2? A length. Which one, L or L0? Oh, excellent. Thank you. We'll get our Timbits next class. Oh, are we first thing in the morning on Thursday? Oh, that works even better. Thank you so much. Meanwhile, the rest, back to my question. What are they asking me to find in question number 2? Oh, in fact, I'm going to argue that question number 2 really is question number 1 done over again. In fact, I'm going to argue that I think I can go like this. And I just got to change some of the things. I think my L0 is different. My speed of light is different. So my L0 is different. My speed of light is different. And my answer is going to be different. So I think my L0 is 45, 98% of the speed of light. 45, 98% of the speed of light. Is that right? I think the physics of this is going to be the same. And I'm doing that on purpose to show you that we can be a little repetitive, but I don't mind that because it's good practice for us. This is some fairly intensive calculator work. Do you all get, 8.95 or 8. If you said 9.0, I'd take that. If you said 8.9, I'd take a half mark off. I'd say round off properly. There's a 5 next to the 9. If you said 8.95, if you said 8.955, whatever. Also on the previous one, if you said 174, I'd also obviously take that. Again, round off properly is all I'm saying. So I'm going to go 8.95. Almost 9 meters long. About 1/5 as long. 45 divided by 9. Yeah, 1/5 as long. You good? Let's keep going. Are they asking me to find M or M0? So the M original, 65. The speed is 99% of the speed of light. The M equation, if you were away last class or you just weren't paying attention, please make sure you add the mass equation to the relativity section of your formula sheet. I'm going from memory. Is it this? It's like the time equation, right? This gamma function feature is on the bottom. Yeah? So it's going to be 65 divided by square root of 1 minus 0.99c over c. Don't forget the squared, Mr. Dewick. Yay, the c's cancel. 65 divided by square root bracket 1 minus 0.99 squared. And Haley, you'll notice I'm trying to do a little bit more in one fell swoop if I can to see how it goes. Let me just pause the video here. Pause. Sorry, when the tech people come by, you take them because they're pretty busy. Jaden, you with me? You're not foolishly on your phone or anything like that, are you? No, you're looking at a calculator. Okay. Okay. Ready, folks? Do you get 461? And that would be the, heavier mass, because Cohen, as you go faster, the mass increases. I would also take, where am I? 460.8. I would take 460 round off properly, same as before. Also, half mark, 1 mark, half mark. Let's keep going. I was saying to someone this morning, yes, I actually looked up the length of the Enterprise. Yes, I actually crunched the numbers so that you will get the actual length of the Enterprise if it did really exist. Yes, I'm that much of a nerd that I had to make the numbers work out okay. So the Starship Enterprise passes you at a speed of 98% the speed of light. You measure its length to be 144 meters. How long is the Enterprise at rest? What's this question asking me to find? What's this question asking me to find? L0. Okay. So I'm going to go L0 equals question mark. And I guess the relativistic length is 144. And the speed is 98% of the speed of light. So the equation that I have right now is L equals L0 square root of 1 minus V over C squared. How would I get the L0 by itself? Yeah. Quick look at money. How would I get the L0 by itself? Divide by what? The big square root? Oh, the Lorentz factor? Thank you for out-nerding me. That was pretty good. Okay. Divide by the square root. So if I hear you correctly, I think I do. You're telling me L0 equals the relativistic length divided by this thing? Cool. Which is going to be 144 divided by the square root of 1 minus 0.98c over c all squared, cross out, cross out. How long is the Enterprise according to the, oh, by the way, this is the Enterprise C from the Star Trek Next Generation, not the original Enterprise, because of course they got larger as the shows got better. Anyways, 144 divided by 1 minus 0.98 squared. 724? Come on. Be consistent in your colors, Mr. Duke. This time, because you had to rearrange the equation, I'd probably give you 1 whole mark for that, half mark for the numbers, half mark for the answer. But again, if you got the right answer, 2 out of 2. A friend borrows your red Ferrari spaceship model X119. Yes, I took this right from the homework. Capable of traveling 95% the speed of light. The Ferrari is measured to be that high and that long. How long would you say the Ferrari was? I think this is asking me to find L, and I think L0 is going to be 18 because the length contraction occurs in the same direction as travel. V is going to be 95% of the speed of light. I think I'm going to end up with this. Oh, wait a minute, Mr. Duick. It's going to be 18 square root of 1 minus 0.95 C over C all squared. Knock, knock. Who's there? C's cancel. Good. 18 square root of 1 minus 0.95 squared. 5.62 meters. And my friend has been gone for 5 hours of my time. How much time does he say has elapsed? Okay, time. Is this asking me to find t or t0? Okay, this was the tricky part. For time, t0 is spaceship time, or in this case, Lamborghini time. So this is asking me to find t0. Time on Earth is 5. Speed that he's traveling at was 0.95 c. So the equation for time was t0 all over the square root of 1 minus v over c all squared. I want to get the t0 by itself. How would I get the t0 by itself? Well, the square root is dividing, so Courtney, I'll times it over. Time on the spaceship, 5 hours of my time, is t square root of 1 minus v over c all squared. 5 hours of my time for him, it's going to end up being 1.56 hours. Half mark, 1 mark, half mark. Turn the page. Is it? Turn the page? Yeah. What speed would an object have to travel to increase its mass from 2 to 4 kilograms? This one's tough. Well, I think they're asking me to find this. I think my original mass is 2. I think my relativistic mass is 4. Mr. Dewick, we don't have a speed equation for mass. No, we don't. Do we have a speed equation for time, though? Because I think these two equations looked identical. It's just wherever you saw an m in one, there was a t in the other. And I'll be honest, I have not memorized this. I know it's v equals c square root of something. I know it's 1 minus. Is it m0 over m, or is it m over m0? Which one? And that's all squared, yeah? Okay. Well, if I have that, it's not too bad. Maybe it's not so tough. It's going to be 3 times 10 to the 8th. There's the speed of light. Square root of 1 minus 2 over 4 all squared. 3 times 10 to the 8th, square root bracket. You know what? I might need a times there. I'm not sure. Square root bracket. 1 minus, well, 2 squared over 4 squared. Or I could have gone 2 divided by 4 is 0.5. I could have just gone 0.5 squared. Regardless, I think as a number you get 25980. That. I'm going to go 2.598. If you said 2.6, I'd take that times 10 to the 8th. Or, if you left it as a percentage of the speed of light, 86.6% of the speed of light. .86c. On your test, if I ask you velocities, which I will, I'll be clear in the instructions whether I want you to leave me the answer as a percentage of the speed of light or whether I want the answer in meters per second. Alex, I will ask you to handle both, though. Okay? A certain star is 40 light years away. How long would it take a spaceship traveling, blah, blah, blah. By the way, I can do part C now using the length equation. I could say the original length is 40 light years. What the heck does the spaceship see when it's traveling at 0.995 C? I can actually get part C without doing part A and part B. I can go L equals L0 square root of 1 minus 0.995 C over C all squared. It's going to be, sorry, let's put the equation down first, Mr. Duick. V over C all squared. It's going to be 40 times the square root of 1 minus 0.995. The C's are going to cancel, Ryan. You will get, using the length equation, 1 minus 0.995 squared. 3.995, heck, if you said 4.0, I'd take that. I'll go 3.995 light years. 3.995 light years. And you can also get that the long way, which we'll do both. Let's go back here. How long would it take a spaceship to reach, measured by stationary observers? Because they're stationary, that's just going to be time equals distance divided by velocity. What distance? 40 light years. What velocity? 0.995 c. C is the speed of light, which sort of cancels out that light there. You end up with an answer, Courtney, in years. It's going to be just a little longer than 40 years because they're almost going the speed of light. 40.2 years as far as Earth is concerned. One mark, half mark, half mark. What about on the spaceship? Well, on the spaceship, we want to find T0. T back on Earth is 40.2. The speed is 0.995 c. Don't forget to put that. So I think when we got the T0 by itself, we said it was times the Lorentz factor over to the other side. It's going to be 40.2 times the square root of 1 minus 0.995 squared, because the C's are going to cancel. Even though, Lindsay, on Earth, we think 40.2 years have gone by, as far as the astronauts on this spaceship are concerned, square root bracket, 1 minus 0.995. To them, the trip is only, 3.995, well, basically 4 years. I'll go 3.995. If you said 4, I'd take that. And because they're traveling almost exactly the speed of light, to them the trip ends up Am I wrong? Yes. Yeah. Oh, I did. So I should get I was wondering why I got exactly the same answer as my one down below, which was making me go, And this does make a difference, I think. Is that better? How about 4.01? That makes more sense to me. Is that right, Sarah? 4.01 years. 4.015, if you really want it to be that fussy. 4.01 years. And so to them, the trip not only seems shorter because of time, it seems shorter because distance is shorter. Half mark, 1 mark, half mark. Now, if you did part C the long way, you could also have gone like this. Or distance equals speed times time. You could have gone 0.995 c times their time, which is 4.01 years, and the light and the years will combine to give you light years. If I take this number and I go times 0.995, I get exactly the same as before, 3.99, I get that number there. So you get same answer, 3.994. Is that what it was? We're rounding off? No, it's still 3.995, I think. Okay. Oh, for this one, half mark, 1 mark, half mark. Can you give yourself a lovely score at the top of this quiz out of, count 'em, 20, please? The next unit. Forces, Newton's laws. Lesson 1, Newton's laws of motion. First, we're going to be talking an awful lot about what a force is. If you want me to be fussy, kinematics, D equals VIT plus a half AT squared, VF equals VI plus AT. Those equations describe how stuff moves. Now we're going to talk about why stuff moves, which is slightly different. A force, it's a push or a pull. Sheldon, there are better mathematical physicsy definitions. In fact, if you go to second or third year university physics, you'll actually say there's only 4 fundamental forces, and all the forces that I'm teaching you are combinations of those, if you really want to go down to first principles and how far you can get, but we're not going to get into that detailed. Force, vector or scalar, most definitely a vector. Direction is going to hugely matter. Hugely matter. Symbol, what would be a good letter to use for force? Capital F. It's a vector, so I'll put a little vector thingy above it to remind myself that it's a vector. Units, force is measured in newtons, symbol capital N, named after a scientist whose last name was Newton. One of the things we're going to start to talk about is the net force. The net force on an object says this: if you replaced all of the different forces acting on something with one, how big and what direction? The net force is combine everything into one. So we're going to start off fairly simple. This says, find the net force in the following diagrams. If I have 7 newtons to the right and 2 newtons, I said 7 newtons, wow, there's a Freudian slip. If I have 5 newtons to the right and 2 newtons to the right, Cohen, what's the net overall force here?
7.
And we'll add a directional component as well. Kevin, you with me? Good. But Sheldon, now we have to start adding vectorially, because although 5 plus 2 is 7, it turns out 5 plus 2 can also give me a different answer. What would 5 newtons right plus 2 newtons left give me? Five plus 2 can also be 3.
Wasn't that just the same as 5 minus 2?
Well, we are adding the forces together. It's just that they're in opposite directions, and we're using negatives to show a direction. What would the net force on this object C be? This is going to be a very important situation. In fact, in particular, it's going to be, if I know the force on an object is 0, then I know the forces have to be balanced, and so I can figure out which forces are missing from my diagram. What about 6 newtons right, and behind you, Cohen? 6 newtons right and 3 newtons up. Well, first of all, because that's in 2 dimensions. But if you're wondering what the answer would be, you would draw a picture. You would draw 6 newtons right, and then on the arrow, you would draw on the end 3 newtons up, and the answer would be that there. You would use Pythagoras to find out how big it is, and then you would use SOHCAHTOA trig to figure out what angle it was at. We do an awful lot of trig. If you take Physics 12, you'll get far better at trig than you ever thought possible. You'll certainly reach the point where SOHCAHTOA becomes so boring and so second nature that in your homework, you can do it without writing anything down. We never will on a test. We always want to show our work to avoid making mistakes. And you might even get that good with the sine law and the cosine law, with c squared equals a squared plus b squared minus 2ab cos theta, and with sine of big A over little a equals sine of big B over little b. We do lots of trig. I may fit some of that in at the end of this year. I don't quite know because I'm redoing the whole course. So what Isaac Newton came along and tried to deal with is the following situation. Let me pause the video for a second. I'm going to go on a bit of a rant here. Newton has 3 laws of motion. I will be asking you to know them, but we'll be flogging them to death so much that you probably will. Newton's first law is often called the law of inertia. It says this. I'm going to phrase it in several different ways, and then we'll do a short version. It says, in the absence of an unbalanced net force, an object will either remain at rest or move in a straight line at a steady or constant speed. The fancy word for that is it won't accelerate. If there's no net force on an object, it can't accelerate. Or if it is accelerating, there must be an unbalanced net force. So the ball illustration, Alicia, that I gave you, since it was slowing down, it was accelerating backwards, but it was accelerating. There has to be an unbalanced force. What? Well, we'll talk about that. But there has to be. There has to be. So if an object is accelerating, which can either be changing its speed, Lindsay, or its direction, or both, there must be an unbalanced I need to type that, force, I need to fix that, acting on the object. Let me give you an illustration. Imagine you're a passenger in a car, and the car makes a rapid left turn. What do you feel during that turn? From your own experience, you might feel like you're getting pushed to the right. That is not what's happening. What's actually happening, because your body, Cohen, has inertia, has mass, it wants to keep going in a straight line at a steady speed. The car door actually applies a force on you to turn you around that corner. And your body feels the door pushing against you. But because you don't think that a door can push, you think you're pushing against the door and getting pushed out. You're not. This is why I said to you, our bodies are backwards accelerometers. They can feel acceleration, but they just feel it backwards. So contrary to what your common sense tells you, you're not being pushed to the right at all. The driver steers the car to the left. Your body wants to carry on in a straight line. But the door of the car is moving left with the rest of the car. You go in a straight line and you actually run into the door, and the door pushes you around the corner. This is the law of inertia. If you talk to your grandfather, he may or may not admit that he knew this as a teenager. Back in the 1960s, when people didn't wear seatbelts and when all the cars had bench seats, guys would go out on a date with a girl, I kid you not, and they would get surfer's wax, and they would wax down the passenger seat, and they would sit like this, and they would make a quick right turn, and the girl would come sliding across. Ask your grandfather, he may fess up to it. If not, he knows friends that did it, and then, oh, hi, honey. Was the girl really sliding across? No, she was going in a straight line. The car was moving underneath her. That's what was going on. Ask your granddad. Anyway, okay. Next page. So, as a rule, an object wants to continue moving with whatever speed and direction it presently has. In fact, we say inertia resists change. Oh, this can include zero speed, of course. So if you're completely at rest, all of you right now are at rest in my room. I can tell you right now the net force on you is 0. Because you're not accelerating relative to the room. Yeah, well, the Earth is moving. Yeah, ignore all that. Just pretend we're standing at rest. Relative to the room, the net force on all of you is 0. Wait a minute, Mr. Duke, isn't gravity acting on me? Yeah, but there must be something acting in the opposite direction of gravity that's exactly the same size. Otherwise, you'd be sinking into the ground. I'm telling you. Okay? So when a driver accelerates the car, your body wants to stay where it is. So you feel the seat pushing against you, which is why I've told you your bodies are backwards accelerometer. It's the inertia of your body that makes your body a backwards accelerometer. So this tendency that all massive bodies have to resist change is given a special name, and it's called inertia. And every object in the universe that possesses mass has inertia. Inertia can be thought as the measure of the laziness of an object. Lazy-iness. I think it's actually going to be spelt like this, Mr. Duke. Or its resistance to change. Newton has 3 laws. Just that one alone starts to explain a lot that you've noticed. What has more inertia, a bike or a logging truck? Be obvious. What does that mean? Sheldon, that is why a logging truck is A, more difficult to get going. If you drive, you'll notice those big semi-trucks suck at accelerating off of a red light. B, more difficult to stop because that's also accelerating and it's got a lot of inertia, a lot of resistance to change, and more difficult to turn around a corner. Now, any person who's ever driven a logging truck has picked that up on their own, Courtney. They've noticed that. Any driver has noticed that semi-trucks behave differently than little Austin Cooper minis. But this is why. It's Newton's first law, the law of inertia. How do we measure inertia? In fact, this year and next year, Lindsay, we're going to say that inertia and mass are the same thing. They technically aren't because at relativistic speeds, weird stuff happens. But you know what? The more mass an object has, the more inertia it possesses. The tougher it is to get it to accelerate, the more it will resist a force. Inertia, or mass, resists a force. In fact, you can think of mass as a measure of the laziness of an object. The more mass an object has, the less willing it is to change its motion state. Cohen, I need to borrow. I wrote down here, magician tablecloth trick. I just showed you how it's done. It also works with tablecloths. You put your phone away, Eric. Thank you. Car accident story. In 1997, during my student teaching, I got rear-ended by a semi-truck on the freeway. I got hit pretty hard. Okay, I was driving a little Honda Civic sedan. And back then, I kept all of my change in my car's ashtray, because back then cars had ashtrays. Sometimes nowadays they don't anymore, but back then they still did. And that ashtray, when I got rear-ended by the semi-truck, went shooting over my shoulder and hit the back seat. Or did it? No. I had enough change in that ashtray that it had enough inertia that it stayed where it was. When I got rear-ended, my car got accelerated forwards. The ashtray stayed where it was, but my car moved forwards. To me, it looked like it went shooting over my shoulder and hit the back seat, but actually, it was a great example of Newton's first law. It wanted to stay where it was. It resisted change. I got some videos to show you. Put your pencils down.